In today's lecture, we are going to see the calculation of energy of a simple harmonic oscillator. Actually, it is a very important problem in simple harmonic motion because you will see that by the energy consideration, we can solve so many problems whose solution is very tedious if we will apply the dynamical method. That is, if you have to prove that motion of a particle or an oscillator is simple harmonic motion and you are following the process of finding equation of motion by finding the forces acting on the oscillator, the solution will become very tedious. But by the energy consideration, such problems can be solved very easily. So this is a very important lecture and watch this video very seriously. And after watching the complete video, I am very confident that you will feel very easy in solving the problems based on simple harmonic motion by energy consideration. So first of all, in this lecture, we will find the total energy of a simple harmonic oscillator. When you say total energy, that means total mechanical energy. And you know, mechanical energy means kinetic and potential energy. Actually, our simple harmonic oscillator will have both kinetic and potential energy, and we will find these two energy one by one, and after adding those two energies, we will get the total energy of the harmonic oscillator. And for this, let us consider there is a particle or an oscillator of mass m oscillating about the equilibrium position O shown in this figure. Okay. And at any moment t, the particle is at this position P, as you can see in this figure, when its displacement is x. Now, if the motion of the oscillator is simple harmonic, then you know when we will consider that when the particle passes through the equilibrium position O and we take t equal to 0 at that moment, then the epoch or the phase constant is 0, as you have learnt in the earlier lecture, and then we can represent the simple harmonic motion of the particle by this equation, that is x equal to a sine omega t, where you know a is the amplitude of the motion and omega is the cyclic frequency of this simple harmonic motion. Now, first of all, we will see what is its velocity at time t. As you know, velocity is simply the time derivative of x. So we can write the velocity of the oscillator at time t, v is equal to dx by dt. And when you will differentiate this a sine omega t, since a is constant and derivative of sine omega t with respect to t will be omega cos omega t. So v is equal to omega a cos omega t. Okay, this is velocity of the oscillator at any time t. Okay, now you can express this velocity as a function of x, and for this you have to eliminate this cos omega t in terms of x, and for this you can use this equation 1. As you can see from equation 1, that sine omega t in terms of x is equal to what? This will be x over a. Okay, and cos omega t by trigonometry, you know this is a square root of 1 minus sine square omega t. Now, instead of sine omega t, we can put x by a. So you can write cos omega t is equal to a square root of 1 minus x square over a square. Now, after taking LCM, this result will be simplified as a square root of a square minus x square over a. Okay. Now, we will substitute this value of cos omega t in this equation number 2, and then you can see your result will be omega A times root over a square minus x square over a. So this a and this a will cancel out, and velocity will be simply omega times root over a square minus x square. Okay. Although we have already discussed these things in our previous lecture. Okay. So you can see we have obtained that V is equal to this much. Now as you can see, since our oscillator has mass and it is in motion, so definitely it will have kinetic energy. So let us see what will be the kinetic energy of this oscillator at time t or at position x. As you know, kinetic energy is simply given by half mv square. Okay. And if your aim is to find this kinetic energy of the oscillator as a function of time, you should replace this V which you have obtained as a function of time here. This is omega A cos omega t. So kinetic energy at time t will be what? This will be half m omega square A square cos square omega t. This is the expression for kinetic energy of the oscillator as a function of time. Okay. Now, substituting this value of V defined in equation 3, we can obtain the expression for kinetic energy as a function of x. So, when we will substitute V equal to this much, then our expression for kinetic energy will be this. This is K equal to half m omega square times A square minus x square. You can see these two expressions for kinetic energy of the oscillator. Equation 4 represents kinetic energy as a function of time, and equation 4a represents kinetic energy as a function of x. And you can see that this kinetic energy of the oscillator during simple harmonic motion is not constant. It varies with time and also with position. Okay, it is variable. Okay. Now, since the oscillator is oscillating under the restoring force, which is just like a spring force, and you know a spring force is a conservative force, and you also know whenever a particle moves under the conservative force, it has interaction energy or potential energy. So our oscillator will also have potential energy, which is in fact elastic potential energy. And you know this potential energy U is given by half kx square. Okay. But you have learnt earlier that the square of the cyclic frequency of oscillator, that is omega square, is equal to k over m. Okay. And so k will be m times omega square. So instead of k, you can write m omega square, and so that potential energy of the oscillator at position x is what? This is half m omega square x square. Okay. Now, this x can be replaced by a sine omega t, as you have seen in this equation 1. So when x will be replaced by a sine omega t, the expression for potential energy will become half m omega square a square sine square omega t. So again you can see this equation 5a represents the potential energy of the oscillator as a function of x, and this equation 5 represents it as a function of time. And both of these equations refer that potential energy is also not constant during the simple harmonic motion. So in this way we have calculated kinetic energy and potential energy of the harmonic oscillator as a function of time t and as a function of position x, and we find that both of these energy vary with time and position. Okay. Now after getting the value of k and u, we will simply add these two energies to get the total energy or the total mechanical energy of the oscillator. So what will be the total mechanical energy? This will be k plus u. So E which represents the total mechanical energy, that will be k plus u. Now let us substitute the values of k and u as a function of x. You have seen that k is half m omega square a square minus x square and u is half m omega square x square. Now this half m omega square x square you can see will cancel out and your result for E will be what? This is half m omega square a square. Now see this equation 6. As you can see, during this free simple harmonic motion, none of the quantities in RHS varies, and so you can say that the total mechanical energy of a harmonic oscillator during the free simple harmonic motion is constant. Okay, it is constant. E is constant. Okay, and actually these things will be discussed later on. First of all, we are going to derive the expression for these energies. Now again, you can get the same result for the energy of the oscillator if you will substitute the values of k and u as a function of t. As you have seen that as a function of t, k is equal to half m omega square a square cos square omega t and u is half m omega square a square sin square omega t. So we can take half m omega square a square as a common factor and the remaining terms will be cos square omega t plus sin square omega t, which is equal to 1. And that's why you can say that E is equal to half m omega square a square. Okay. So these are the expressions for kinetic and potential energy, and you have seen both kinetic and potential energy varies with position, with time, but total energy remains constant. So energy of a simple harmonic oscillator during a free simple harmonic motion does not change. It remains constant. Okay. But when we will talk about this energy consideration in damped harmonic oscillation, then you will see that energy of the oscillator will not remain constant in damped simple harmonic motion. But in free simple harmonic motion, total energy of the oscillator remains constant. That is, there is no dissipation of energy, since in this case there is no dissipative force acting on our oscillator. Now we will discuss these results which we have obtained just now. And in this discussion you will see so many facts which are very helpful, very useful for answering all those questions asked in different examinations. Even in competitive examinations and university examinations, the problems based on this energy consideration of simple harmonic oscillator can be solved very easily if you will watch all the discussions, all the important facts which I am going to discuss here. As you can see, that the expression for kinetic energy is half m omega square a square minus x square. So you can see when x will increase, it is obvious from this result that this k will decrease non-linearly because x contains power 2, so the variation will be non-linear. Okay, and at the same time u is equal to this much, half m omega square x square. Can you say that how this u varies with x? This is just a standard equation of a parabola, y equal to 4ax square. The parabola which is symmetrical about the y-axis, that is represented by this equation, and this equation for u is same like this. So you can say that this u will vary with x in a parabolic manner with increase in x. That is, when you will move from the equilibrium position to the extreme position, x will increase, and with increase in x either in positive direction or in negative direction, u will increase non-linearly. Okay, but and total energy of the oscillator will not change, it remains constant. So in the first point I have written that with increase in x, that is when the particle moves from the equilibrium positions to the extreme position, then potential energy increases non-linearly, kinetic energy decreases non-linearly, but total energy remains constant. Okay, I think this fact is very clear to you. Now we will see what will be the values of these energies at some important or you can say standard positions. You know, during simple harmonic motion, there are two very important or very standard positions. First one is the equilibrium position and another are actually the extreme positions. Okay. You know, when you are saying equilibrium position, and as you know, we measure the displacement of the oscillator with respect to the equilibrium position. So when the particle or the oscillator will be at its equilibrium position, x will be 0. And so substituting x equal to 0 in all the above expressions for k, u and e, we can get the value of these energies when the oscillator is at equilibrium position. So let us see. As the expression for kinetic energy is what? This is half m omega square a square minus x square. And here we will substitute x equal to 0, which is the minimum value of x. So when you will subtract minimum, you will get maximum. That's why we simply say that at the equilibrium position, kinetic energy will be maximum, and this maximum value will be what? This will be half m omega square a square. Half m omega square a square, as you can see from this figure after from this equation after substituting x equal to 0. And this expression is nothing, this is the total energy. So you can also say that the maximum kinetic energy is equal to total energy. Okay. And potential energy, as you have seen that potential energy is U equal to half m omega square x square. So when you will put x equal to 0, this potential energy will be 0, and it is the minimum value of the potential energy. But total energy will remain same because it does not depend on x, and so total energy E is half m omega square a square, and it is equal to the maximum value of kinetic energy. So it is evident here that at the equilibrium position, the total energy of the oscillator remains in the form of kinetic energy. There is no potential energy when the oscillator is at its equilibrium position. Okay, 100% energy is in the form of kinetic energy. Okay, I think this point is clear to you. Now let us see. When the particle will be at its extreme position, either at the positive extreme position where you take x equal to a, or at the negative extreme position where you take x equal to minus a. What will be then these energies? So at the extreme position, x is equal to plus minus a, which is actually the maximum value of the displacement. So for getting energy at these positions, we will simply substitute x equal to either plus a or minus a in these two expressions. And you can see when you will put x equal to a or minus a in the expression of kinetic energy, this a square minus a square will cancel out. And so kinetic energy at the extreme position is 0. It is obvious because at the extreme position, you know, velocity of the oscillator becomes 0. So it is obvious that kinetic energy will be 0 at the extreme position. And so it is the minimum value of kinetic energy. Okay. But since potential energy is directly proportional to x square and x is maximum, so at the extreme position, potential energy will be maximum, and that is equal to half m omega square a square. And as you can see, this is equal to the total mechanical energy. Okay, so you can say just opposite to the equilibrium position, at the extreme positions, the 100% energy of the oscillator is in the form of its potential energy. There is no kinetic energy in the oscillator at the extreme position, and total energy is simply in the form of potential energy. Okay, so these two facts are very important for objective questions. Okay, now you can see I have shown in this figure how the potential energy and the kinetic energy varies with x. As you have seen that these two functions k and u varies with x in parabolic manner. So definitely the graphical plot of k or u in against of x will be a parabola symmetric about this k axis or u axis or e axis. Actually in this figure I have noted kinetic energy, potential energy and total energy on this y axis, and the displacement x has been written on x axis. Okay, you can see when x is 0, you have seen that potential energy is 0. So this curve which passes through this origin is represent the potential energy. And at x equal to 0, since kinetic energy is maximum, and you can see this point P in this figure which represents the maximum value of energy, which is equal to half m omega square a square. Okay, so and when x increases, then potential energy non-linearly increases in parabolic manner, and when x is equal to plus a, then potential energy is maximum. So this first curve represents the variation of potential energy. But at the same time, with increase in x either in positive direction or in negative direction, kinetic energy decreases and becomes 0 at this position where x is equal to plus a. So here kinetic energy is minimum, that is 0. Okay, and here also it is 0. So this second curve represents the variation of the kinetic energy. And you can see this straight line which is parallel to x-axis, this represents the total energy and it remains constant. Okay, you can see in this figure that these are the points. Let us say this is point P1 and this is point P2, where these two curves for u and k intersect one another. And at the point of intersection, what will be the potential energy and kinetic energy? Actually, at this point of intersection, both will have same value, and you know the total energy is constant, and k and u both are same. So it means at this point of intersection, kinetic and potential energy both will be equal to half of the total energy. Okay, so I have mentioned it in this figure, you can see. So how k, u and e varies with x, you can see in this figure. Okay, now we are going to see a very important fact regarding this simple harmonic oscillator here by the energy consideration. Actually, when an oscillator performs simple harmonic motion and you calculate its kinetic energy and potential energy as a function of time, you can see that both of the kinetic and potential energy of the oscillator varies in periodic manner with time. In other words, you can say that kinetic and potential energy vary periodically, and the frequency of the oscillation or variation of both k and u are same, and its frequency, if you consider that the frequency of variation of k and u are omega dashed, it will be twice of the frequency of the simple harmonic motion. It means k and u vary periodically with a with double frequency of simple harmonic motion. And when its frequency will be 2 times of the frequency of simple harmonic motion, then its time period, this will be just half of the time period of simple harmonic motion. So this is a very important fact, that the frequency of kinetic and potential energy is twice of the frequency of simple harmonic motion, and time period of the kinetic and potential energy, that will be just half of the time period of the simple harmonic motion. But one thing is also interesting here. Although kinetic and potential, both energy vary periodically, but not simple harmonically. It means these two quantities are not itself simple harmonic. Okay. So we will now see the explanation or the proof of this very important fact. Okay. First of all, we will show that K and U vary periodically with a frequency of twice of the frequency of simple harmonic motion, or time period of half of the time period of simple harmonic motion. First of all, we will explain this. And for this, let us see the expression for the kinetic energy of the oscillator as a function of time. And you have seen that K is equal to this much. This is half m omega square a square cos square omega t. Okay. Now, instead of cos square omega t, you can write 1 plus cos 2 omega t divided by 2. You have definitely learned, studied this in your course on trigonometry. Okay. And this half m omega square a square, what is this? Can you say? This is the total energy. So instead of half m omega square a square, you can write E. So this expression can be written as K equal to E over 2 times 1 plus cos 2 omega t. Okay. Now instead of 2 omega, you can write omega prime. So the expression for kinetic energy is what? This is half E 1 plus cos omega prime t. So this expression for kinetic energy is what? This is E over 2 plus E over 2 cos omega prime t. Observing this very equation for kinetic energy as a function of time, can you say how this kinetic energy is varying with time? It varies in accordance with the cosine function with a frequency omega prime, which is equal to 2 omega. And as you know, cos theta is a periodic function, and cosine function varies periodically. So we can say that kinetic energy varies with time in periodic manner in accordance with the cosine function, and the frequency of its variation, if it is denoted by omega prime, that is simply equal to 2 omega, where omega is the frequency of simple harmonic motion. So the first fact, that kinetic energy varies periodically with double frequency of simple harmonic motion, has been proved. Okay, I think you have clearly understand. Now in the similar manner, you can see that the same fact holds for the potential energy too, as U is equal to half m omega square a square sin square omega t, and sin square omega t can be written from this formula as 1 minus cos 2 omega t over 2. Okay. So U can be written as half m omega square a square times 1 minus cos 2 omega t over 2. And again, at the place of this half m omega square a square, you can write E. So the expression for the potential energy of the oscillator is 1 over 2E times 1 minus cos omega prime t. Here omega prime has been again written for 2 omega. Again you can see this potential energy also varies with time in periodic manner, because this equation contains the cosine function with the same frequency omega prime, which is twice of the frequency of simple harmonic motion. So the first part of the above fact has been proved, in which we have shown that the kinetic and potential energy of a linear harmonic oscillator varies periodically with time and with a frequency which is twice of the frequency of simple harmonic motion. Now, as frequency is twice, so time period will be just half, because if you want to find the time period of a simple harmonic oscillator, which I have denoted by the symbol T prime, what will be this? This will be 2 pi over omega prime. Okay. But omega prime, you have seen this is 2 omega, and now this becomes 2 pi over 2 omega. But 2 pi over omega, this is the time period of simple harmonic motion. So the time period of variation of kinetic and potential energy is T over 2, where T is the period of simple harmonic motion. So you can say that the kinetic and potential energy varies with a time period which is just half of the time period of the simple harmonic motion. So this fact has been very clear to you, as I hope. Okay? Yes or no? Definitely you should say yes. But now I am going to explain how we can say that during simple harmonic motion the kinetic and potential energy of an oscillator varies periodically with time, but this variation is not simple harmonic. How we can say? Now I am going to explain this fact. As you know, any quantity, let us say psi is a variable or psi is a function, you should say, and this is a function of t, let us say, okay, psi is function of t. Then the variation of psi will be simple harmonic. What is the necessary and sufficient condition for it? You have learnt in the definition of simple harmonic motion that if any function psi which is a function of t, this will vary simple harmonically, or its variation will be simple harmonic. The necessary and sufficient condition for it is what? It is its second order time derivative, that is d2 psi by dt square. This should be proportional to minus psi. This is actually the necessary and the sufficient condition for psi to be simple harmonic. Okay. As you have seen in the equation of simple harmonic motion, where we see that d2x by dt square is equal to minus omega square x, where omega square is constant, and you simply say that this d2x by dt square is proportional to minus x. Then you say that this x varies simple harmonically. Okay. So if your aim is to prove that k and u do not vary simple harmonically, you should find its second order time derivative, and you should see that either it is proportional to minus k or minus u or not. You have to show this. So if kinetic energy will not vary simple harmonically, then definitely we have to show that d2k by dt square is not proportional to minus k. If you are able to prove this, then you can prove this fact. And similarly, if we will show that d2u by dt square is not proportional to minus u, then we can say that the variation of u is not simple harmonic. And for this, let us try to obtain the second order time derivative of these two energies. As you know, k is equal to what? This is half e times 1 plus cos omega prime t. So you can find dk by dt, and this will be this much. This differentiation is very easy, you can see it. And after that you will obtain d2k by dt square, and that will be minus omega prime square times e by 2 this much. You can see that the RHS, which is minus omega prime square, and the remaining factor is e by 2 cos omega prime t. Is this expression e by 2 cos omega prime t equal to k? Answer will be no, because you have seen that k is equal to e by 2 plus e by 2 cos omega prime t. So this expression is not equal to k. If it will be equal to k, then you can say that d2k by dt square is proportional to minus k. But since this expression is not equal to k, so we can say that d2k by dt square is not proportional to minus k. And if it is not proportional to minus k, we can easily say that the variation of k is not simple harmonic. Okay. In the similar manner, you can see after differentiating 2 times the expression for u, you will get d2u by dt square equal to this much. And again here you can see that d2u by dt square is not proportional to minus u. So finally, after this, we can conclude that in simple harmonic motion, the kinetic and potential energy of the oscillator varies periodically with time, with a period just half of the period of simple harmonic motion, or with a frequency twice of the frequency of simple harmonic motion. But this variation of k and u is not simple harmonic. Itself k and u are not simple harmonic. Okay. I think this fact is now very clear to you. This is a very important fact for your objective questions. Okay. Now we will talk about the average value of kinetic and potential energy. As you know, in physics and mathematics, we always talk about average or mean value when our quantity varies. Okay. And you have seen in this lecture that both the kinetic energy and the potential energy varies with time. They are functions of time and position. So we can find the average value of k and u for a given time interval, because average is always defined for a particular interval. Here we are going to find the average value of potential energy and kinetic energy in a time interval which is between t equal to 0 and t equal to capital T, where capital T is the period of simple harmonic motion. And as you know, from the idea of how we find the average value of a variable quantity, whenever you have to find, let us say y is a variable quantity which depends on x, and you have to find the average of y between interval x1 and x2. Then the general expression for finding the average value is what? This will be integral y dx from x1 to x2 divided by this interval x2 minus x1. This is the general concept for finding the average. So the average value of kinetic energy between interval t equal to 0 and t equal to t, what will be that? That will be integral k dt from 0 to capital T divided by capital T minus 0. Now let us substitute the value of k. As you have seen that k is equal to this much. This is e over 2 times 1 plus cos 2 omega t. Here I have not written omega prime, but omega, instead of omega prime I have written 2 omega. Okay. Now e by 2 is a constant factor, so it will be outside of the integral. And we have to integrate 1 plus cos 2 omega t. And this integral is this much, you can see, and limits are 0 and t. Now let us put the limits. When you will put the limit at the place of t, there will be capital T, and here in second term, this will be 1 over 2 omega sine 2 times omega t. But omega is 2 pi divided by capital T, and instead of t, we will now write t. Now this t and this capital T will cancel out, okay? And when we will put the lower limit, both of the terms will become 0. So I have written here directly 0. Now again you can see this second term contains sine 4 pi, and you have definitely an idea that sine n pi is equal to 0, where n may be 0, 1, 2, 3, 4 and so on. So this second term inside this square bracket is also 0. So only the non-zero term is this capital T. So the average kinetic energy will be E over 2t times t plus 0, and this t and t will cancel out, and you can see the average kinetic energy is E over 2. But E is half m omega square a square, so this is 1 over 4 m omega square a square. So you can see that in an interval equal to the period of simple harmonic motion, the average value of kinetic energy of the oscillator is just half of the total energy. This is the average value. And in the similar manner, you can see the average value of potential energy will be also same. And for this, you will substitute the value of the potential energy here in this expression, and after calculation in similar manner, you will get that average value of potential energy of the oscillator in an interval just equal to period of the simple harmonic motion is also E by 2, and so you can say that during simple harmonic motion, the average value of kinetic energy and the average value of potential energy in an interval equal to the time period of simple harmonic motion is simply equal to half of the total energy of the oscillator. Okay? So this is a very important fact, and you should remember it too for solving your objective questions. Okay? Now finally we are going to see how we can obtain the equation of motion of simple harmonic motion by the energy consideration. Okay? And as I have told you earlier, that this idea is very helpful in solving some of the numerical problems whose solution becomes tedious by the dynamical method. As you know, in simple harmonic motion, total energy of the oscillator remains constant. So I have written here E is equal to constant, but E, you know, this is K plus U, and that will be constant. Now in general, K is half mv square, and at the place of V I have written dx by dt, okay, and U is equal to half kx square. Okay, so this is the general expression for energy. Now we will differentiate this equation with respect to 2 to get the equation of motion of simple harmonic motion. Okay, and you can easily differentiate it. Since half m is a constant factor, so during differentiation it will be outside of the operator, and we will have to differentiate dx by dt whole square. This is just a function of function. You know, dx by dt whole square will be first of all differentiated with respect to dx by dt, and that will be 2 into dx by dt. Okay, and then dx by dt will be differentiated with respect to t, and that will be d2x by dt square. Okay, now again half k is constant, and we will differentiate x square with respect to t. This is also a function of function, and this derivative will be 2x times dx by dt. Now see here, this 2 and this 2 will cancel out, this 2 and this 2 will also cancel out, okay? And we can take dx by dt as a common factor. Then the remaining factor will be what? This is m d2x by dt square plus kx equal to 0. But as you know, this dx by dt, which represents the velocity of the oscillator, this is not 0 at all time. Only at the extreme position this velocity is 0, and other than the extreme positions it is never 0. So definitely you can say that the expression inside this square bracket will be 0. So we will equate this m d2x by dt square plus kx equal to 0. Okay, and when you will take m as a common factor, the result will be d2x by dt square plus k over m into x equal to 0. Again, this m is not 0, so the factor inside this square bracket will be 0, and this represents simply the simple harmonic motion. So I have written it here. You can see that d2x by dt square plus k by m into x is equal to 0. And instead of k by m, you can write omega square. Okay. So, and you can see this is just the equation of motion of simple harmonic motion. And so in this way, by the concept of energy conservation, or energy remains conserved during simple harmonic motion, we can obtain the equation of motion of SHM. Okay, so I think you have clearly understand all the concept which I have discussed in this lecture, and definitely you have enjoyed. Thank you very much.